Hi, welcome to this lecture on Google's PageRank algorithm. Here's the outline for this lecture. We'll first talk about the RandomSurfer model, which is a very useful model that allows you to study certain properties of the World Wide Web. And then we will discuss a file format for representing the World Wide Web as a graph. And then we will discuss an important concept of the transition matrix. And then we will talk about how you simulate a RandomSurfer on a graph representing the World Wide Web using the transition matrix. And then finally we'll talk about a concept called Markov Chain and how you use that to implement an algorithm, an efficient algorithm for figuring out page ranks. So what is the RandomSurfer model? So the RandomSurfer model is a very simple model of the World Wide Web that has proven to be very useful in understanding some of the properties of the World Wide Web. Now we're going to model the World Wide Web as a graph, meaning as a fixed set of pages with each page containing a fixed set of hyperlinks. Right? And each link is basically a reference to some other page. And this abstraction is what we call a graph in mathematics. So a graph is nothing but a collection of points, which in the case of the World Wide Web denote HTML pages. And then a graph also has edges or connections between these points. Okay, so there are all these like pairwise edges. And in the context of the World Wide Web, these edges denote hyperlinks. So these edges are all directed links, directed edges. And what it means is that there is, for example, a hyperlink that points from this page to this page, and hence an arrow going in that direction. Similarly, there is a hyperlink from this page to this page, and hence this directed edge. And if there is a hyperlink from this page to this page, you would have an edge that looks like that. Okay, so we're going to model the World Wide Web simply as a directed graph where the vertices or these points represent HTML pages and the edges or the links represent the hyperlinks from one page to another. Okay, and what we're interested in is what happens to a person that we call the RandomSurfer who randomly moves from one page to another on this graph representing the World Wide Web. Okay, so we have a graph representing the World Wide Web with a certain number of pages, certain number of links, and we drop a random individual, a RandomSurfer, on some page on that graph and let that surfer hop around from one page to another. Okay, and in hopping around the we're going to use what is called the 90-10 rule. And which means that 90% of the time the RandomSurfer is simply going to click on a random link on the current page and jump to the next page, okay, just by following that random link. So that's what the surfer is going to do 90% of the time. So just follow links from one page to another. Okay, and 10% of the time the RandomSurfer is going to go to a random page on the web by simply typing the address of that page on the address bar. Okay, so that's the 90-10 rule. 90% of the time the RandomSurfer will just follow a link from one page to another, and 10% of the time the surfer will go to a random page by typing the address in the address bar. Okay, there is nothing magical about these numbers 90-10. You can try other splits as well, such as 80-20 and so on, but this is what has worked out very well. Okay, so that's what people generally do, implement the 90-10 rule. Okay, and now what we want to figure out is this notion of a page rank, and the page rank is simply the probability that the RandomSurfer lands on a particular page. Okay, so we have our graph representing the World Wide Web, and the random surfer is just hopping around from one page to another. So let's say we give the random surfer t number of hops, all right? And then what we do is we simply keep a tally of the number of times the surfer landed on each of the, let's say, n pages. Okay, so and that number, that frequency, is going to represent the popularity of that page, meaning how many times out of the capital T number of times did the surfer land on a particular page. That number, that frequency, is going to represent the popularity or the page rank of that page. Okay, so this was essentially Google's insight. Okay, so the two individuals, the founders of Google, Larry Page and Sergey Brin, they came up with this idea as part of their PhD thesis. Okay, and this was completely novel because back in the day, before Google, the way search engines operated was simply, to take the search terms that you enter in the search engine and compare those with a database of HTML pages that the search engine tracked. And then the search engine would simply report on all those pages that had your search terms. Okay, so it would simply list them. And what Google did in addition to that was to list those pages in order of relevance. Okay, so how does Google figure out the relevance of a particular page? Well, it uses the idea of a page rank, okay, which simply depends on how many times a random surfer lands on a particular page. Okay, and it's a very interesting idea because the relevance of a page simply depends on the structure of the World Wide Web. All right. And a page is more popular if there are many other pages pointing to it. Okay, so that was Google's insight, and it was very different from how search engines handle things prior to Google. Okay, and that's the idea that got Google very successful as a search engine. Okay, and the two individuals, Sergey Brin and Larry Page, who came up with this idea, they became instantly famous and instantly rich, right? Because of this idea. So in this lecture, we're going to talk about how we figure out this page rank, right? So given a graph representing the World Wide Web, how do we compute the relevance of each page in the World Wide Web, or the page rank of each page? All right. Now let's look at a file format for representing a World Wide Web as a graph. So what is shown here is a tiny web consisting of 5 pages, right? And these pages are labeled 0 through 4. So each circle is a vertex or an HTML page in the World Wide Web, and they're simply labeled with numbers 0, 1, 2, 3, and 4, right? And what you see as arrows are basically the hyperlinks from one page to another. So this arrow here denotes that there is a hyperlink from page 4 to page 0. This arrow here says that there is a link from page 0 to 1. These two arrows say that there are 2 hyperlinks from the page 1 to the same page 3. And that's very realistic. I mean, you do see that a lot in the real World Wide Web, and so on. Okay, so this is a very simple example of a tiny web. Now the question is, how do we represent this web or graph as a file? Okay, so that later on we can write Python programs that use that file as input, okay, and calculate certain properties such as page ranks for that World Wide Web. So the format is going to be extremely simple. So here what I'm showing you is a file called tiny.txt, and I'm just showing you the contents of the file. So more is a Unix command that simply displays the content of the given file. So the very first line that you see is the number of pages in the World Wide Web that is modeled by this file. In this case, it is 5. Okay, so the number of pages, which we denote by capital N, is 5 in this case. And then after that, you simply see these pairs of numbers representing the hyperlinks. So 0, 1 means it is a hyperlink from page 0 to 1. That's this link. And then you have two pairs, 1, 2, 1, 2, representing these two hyperlinks, right, from page 1 to page 2. And then you have two hyperlinks from 1 to 3. So that's these two guys. And then you have a hyperlink from 1 to 4. That's this one here. And then you have a hyperlink from 2 to 3. That's this guy. And then you have a hyperlink from 3 to 0, which is this guy. And then you have a hyperlink from 4 to 0, which is that, and 4 to 2, which is that. Right? So this file completely captures this World Wide Web. Right? So that's going to be our representation of a World Wide Web as a very simple file. Now let's talk about a very important concept, which is that of a transition matrix. So transition matrix, denoted capital P for a World Wide Web with n pages, is simply an n by n matrix which has n rows and n columns, right? And n is the number of pages in the World Wide Web. So what are the entries in this matrix? So the entries are denoted as P sub ij, and this entry is basically the probability that the random surfer moves to page J while on page A. All right, so you have your transition matrix P, which has n rows and n columns. And if you focus on a row I and a column J, then the cell there is what we denote by Pij. Okay, and that is simply a probability. It's the probability that the surfer, while on page I, will end up on page J in the next move. Okay, so it's simply a probability that the random surfer moves to page J when on page I. And since it's a probability, it's going to be a number between 0 and 1. So this number here is between 0 and 1. All right? Okay, so for the example that we just saw, the tiny web with 5 pages, the transition matrix is what is shown here, right? So P for that tiny web is a 5 by 5 matrix, okay? And each element here is the probability of going from one page to another in the next move. So for example, so these guys are going to be indexed 0, 1, 2, 3, and 4, 0, 1, 2, 3, and 4. So if you focus on this particular number here, what is it? Well, it's the probability that the random surfer, while on page 4, will end up in page 2 in the next move. Okay? What is this number here? That's the probability that while on page 3, the random surfer will end up on page 0 in the next move. Okay? So that's how you interpret these numbers. And then keep in mind that this matrix is somewhat special. It's called a stochastic matrix, and so in such a matrix, the rows all add up to 1. So these numbers add to 1, these numbers add to 1, these numbers add to 1, and so on. So every row adds up to 1 in such a matrix. Okay. Now, so given a graph that represents a World Wide Web, there is a unique transition matrix for that graph. And for the 5-page example that we saw, for the 5-page World Wide Web that we saw in the previous slide, this is the transition matrix, right? So the question is, how do we get this transition matrix? How do we compute it given the graph representing the World Wide Web? So that's what we're going to talk about next. So here what we are looking at is a program called transition.py, and this is the program that computes the transition matrix for a given graph or World Wide Web represented as a graph. Right? So what is the input and what's the output? Well, the input is a representation of the World Wide Web as a graph, and the format that we're going to use is what we discussed before. Okay, so the input, which is a graph representing the World Wide Web, is going to be supplied to this program via standard input. Right? And what is the output of the program? Well, the output is a transition matrix, which is an n by n matrix. Okay, and in order to compute the transition matrix from the input graph, we make use of the 90-10 rule that we discussed before. So recall that the RandomSurfer just follows hyperlinks 90% of the time, and 10% of the time the RandomSurfer goes to a random page. Okay, so we're going to use that idea to compute the transition matrix from the input World Wide Web. So let's go through this program. We import two modules, stdarray and stdio. These are familiar modules. And then the first thing that we do is read from standard input an integer that we call n. So if you remember the input format, this number is going to denote the number of pages in the input graph representing the World Wide Web, right? So n pages. And then what we do is we create two lists. The first list is called link counts, and that has size n by n, so it's a matrix, and everything is initialized to 0 to begin with. Okay, so we are making use of the create2d function from stdarray to create an n by n matrix with everything initialized to 0. What's the interpretation of this matrix or this 2D list called link counts? Well, it's n by n. Okay, and if you focus on a particular row I and a particular column j, what do you see in that matrix link counts? Well, this number here is going to denote the number of hyperlinks from I to j, from the page I to the page j. That's what each element in this matrix stores. Okay? It's simply the number of links from page I to page j. What about this list? So out degrees is created as a single, as a one-dimensional list of size n, and everything is initialized to 0. So what are the values in out degrees? So out degrees is a one-dimensional list, so it simply looks like that. It has n elements, and if you focus on a particular element here, that number is simply going to be the number of links from the page I. Okay, simply the number of outgoing links from the page I, and that's what we call out degrees. All right, so that's how we interpret these two lists. Okay, and then what are we doing in this while loop? So in this while loop, we read from standard input pairs of numbers ij. Okay, and if you recall the format, what is this pair? This pair is simply saying that there is a link from I to j, from the page I to page j. Okay, so as long as standard input is not empty, we read a pair of integers ij, and then once we read this pair ij, we know that there is a link from I to j. Okay, which means there is another outlink from I, right? So we simply go to the index I in out degrees and increment it by 1, because we just saw another link that leaves I. So we update out degrees as such. And since this is a link from I to j, we go to the ijth entry in link counts and increment that by 1. Okay, so these two updates make perfect sense. Let me repeat. Since we are seeing a hyperlink from I to j, we increment the out degree of I by 1. And then since this is a link from I to j, we increment the ijth entry in link counts by 1. So once this while loop is done, all the input has been processed, meaning we have read the graph representing the World Wide Web, and we have populated these two lists, link counts and out degrees, these two guys. Okay, they are completely filled in with the right values. Okay, now, so the last thing that we need to do is compute and print the transition matrix. But before that, we simply write the dimension of the transition matrix, which is n by n. So all that we are saying here is that the transition matrix that we're going to write has dimensions n by n. All right? Okay. Now let's see how we compute and write the transition matrix. Since we are writing a matrix out, we need nested for loops. So I goes from 0 all the way up to n minus 1, and for each such I, j goes from 0 through n minus 1. Okay? Because we are dealing with an n by n matrix. Okay, and here what we are doing is we are calculating this value pij. So p, little p, is simply pij. It's the probability of going from page I to page j in the next move. And this is where the 90-10 rule comes in. So we are saying that 90% of the time, the random surfer will simply follow a link. So it's 0.9 times link counts of ij divided by out degrees of I. Now convince yourself that this expression is correct. So larger the value of link counts ij, it means the higher the probability of going from page I to page j, right? So we want this expression in the numerator, because if there are more links that will get you to page j from page I, then you're more likely to end up on page j. So it makes sense that this expression is in the numerator. What about this expression in the denominator? Well, if there are many links leaving from I, then that dilutes the probability of going to a particular page j. Okay, so that's why it makes sense to have out degrees of I in the denominator. Okay, so that's basically the 90 part from the 90-10 rule. And then this part says that about 10% of the time the surfer goes to a random page out of the n pages. Okay, if there are n pages, and if 10% of the time you go to any one of those, then the probability of going to any one of those pages is 10% divided by n, right? So that's the 10 part from the 90-10 rule. Okay, so P is this probability Pij, the probability of going from page I to page j. Now what do we do with that value? We simply write it out, and we write it out using this format up to 5 decimal places. Okay, all right, and then we keep doing this, and once an entire row is written, meaning once j is exhausted, we write a new line character. Right? So that the next row shows up on a new line, right? So once the for loop is done, the entire transition matrix has been written out, right? So that's how we compute the transition matrix using the 90-10 rule and simply write it out. So let us look at some input and output. So here I run transition.py with tiny.txt representing that tiny 5-page web from a previous slide. And I'm feeding that file as standard input to the program, right, using the redirection operator. And what does the program do? Well, it prints the transition matrix. It first prints the dimension of the matrix, which is 5 by 5, and then it prints the transition matrix itself. And this is the matrix that we saw in a previous slide, okay? The transition matrix for this very simple 5-page web. And what is each number here? Each number is the probability of going from one page to another. So that number is the probability of going from page 3 to page 2 in the next move. All right? Okay, so now let's talk about this program, RandomSurfer.py, that simulates a random surfer. All right? Now the input for this program is going to be a command line argument called moves. So moves is going to denote the number of moves that you're allowing the random surfer, the number of hops, the total number of hops, right? And in addition, there is going to be some standard input, which is the transition matrix, right? So the transition matrix is going to be fed via standard input, right? And what are we simulating here? Well, we are simulating a random surfer navigating around in the World Wide Web, right? using this transition matrix. So the surfer is going to start on some page and simply hop around for a total of these many moves, okay, using the transition matrix. And then at the end, what we're going to do is we're simply going to report the frequency of hitting each page, meaning how many times out of the moves number of hops did the surfer land on each of the n pages. Okay, and that number or that frequency is the PageRank. So this program simulates the random surfer on a World Wide Web and reports the page ranks. All right, so let's walk through the program. We import all these modules: random, std, array, stdio, and sys. We get the command line argument moves as an integer, and then what we do is we read the transition matrix. Okay, so all this code here reads the transition matrix into memory. Okay, so how does that work? Remember that the previous program, transition.py, which calculates and prints the transition matrix, what it does is it first prints the dimension of the matrix. Okay, so that's why this program first gets the dimension. So n is simply an integer read from standard n, right? And then we do another call to read int because it's a two-dimensional matrix, right? So it's n by n. So if you recall, transition.py reported two numbers as the dimension of the matrix, right? And that's what we are reading here. This guy and this guy, right? And then notice here that we don't assign the return value to any variable. We don't need to, because this is a square matrix. We've already figured out the number of rows, and the number of columns is exactly that. We don't need another variable, okay? But we do need to read it though, right? Because that is part of the dimension. All right. So once we know the dimension of the transition matrix, what we do is we create a 2D list called P using this function create2D that has n rows, n columns, and everything is initialized to 0. So this is going to be the transition matrix. And then in these nested for loops, we are simply populating that matrix. So I goes from 0 through n minus 1, and for each such I, j goes from 0 through n minus 1. And we say that the ijth element in P is simply a float that is read from standard input. So what we are doing here is consuming the transition matrix that was produced by transition.py, the previous program. Okay, so once this for loop is done, we have the entire transition matrix in memory as an n by n matrix, right? Okay, so that's the first part, and then the next part is to simulate the random surfer, right? So what we do first is create a one-dimensional array called hits of size n, everything initialized to 0. So hits is basically going to store the frequency of hitting each page, all right? So out of the moves number of hops, how many times did the surfer land on page 0, on page 1, on page 2, and so on, all the way up to page n minus 1. That's what is going to be stored in hits. So it's simply the frequency of hitting each page. Okay, so everything is initialized to 0 so far because we haven't yet started simulating this, the random surfer. Okay, and then we say that the surfer starts on page 0. Okay, it doesn't really matter where you start the surfer. You could start the surfer on any page between 0 and n minus 1, but we decided here to start the surfer on page 0. Okay, and then we allow the surfer moves number of hops. So I goes from 0 through moves minus 1. That's that. And then what are we doing here? This is where we are figuring out where is the surfer going to end up. All right, so the surfer is currently on the page that is given by this variable page. So where is the surfer going to end up next? All right, and that's a random process, right? So how does that work? So before we look at the code here, let me walk you through this figure, right? So we're going to assume here that page has some value, let's say 4, right? So the surfer is currently on page number 4. So the question is, where is the surfer going to end up next in the next move? So this is where we need to consult the transition matrix, right? So if you go to the transition matrix and look at row 4, you will see this row there, this slice, All right. So these are basically the probabilities of going from page 4 to any of the other the pages in the World Wide Web, which are 0 through 4. Okay. So the question is, which one does the surfer go to? Well, that's a random process. So how do we figure out? We get a random number between 0 and 1, okay, and then recall that all these numbers add up to 1. Okay, so when we get a random number, it's going to be between 0 and 1. Okay, so that is going to be between here and here. All right, so let's say for the sake of argument that it came out as 0.71. So it's somewhere there. So the question is, which slot did it land? So these are all slots. So one slot, second slot, third slot, fourth slot, and fifth slot, representing each of the 5 pages. And the width of the slot is dictated by the probability value. So 0.47 is much wider than 0.02, which is this guy. And this is 0.47 again, much wider than the other slots. Okay, so the width of the slot is dictated by the probability value. Right? So we need to figure out which slot did this random number land on, and that's the page that the surfer is going to jump to. Okay, so that's what we are doing here. We are getting a random number, which is a number between 0 and 1, such as 0.71, and then we say total equals 0. All right, so total is initially 0, and then what we do is j goes from 0 all the way up to n minus 1, right, because there are n pages, and then we say the new value for total is the old value of total plus the probability given by this entry, page j. Okay, so we simply take a value from here, from this particular row, so page j, and add it to total, right? And what we do is now we compare total versus with R. Okay, now if R is less than total, what it means is we have identified the slot where the random number landed. Okay, but if total on the other hand is less than or equal to R, then we still haven't reached here. So in that case, what we do is we keep doing this. We get the next value, append it to add it to total, and then do this check again, right? But once this condition is satisfied, so once R is less than total, we know that we have identified the slot where the random number lands. So we say the new value for page is simply that slot, the j, the jth slot. Okay, and we break out of the for loop because we have identified the page where to jump to. And since we now are going to end up on that page, we say hit set page plus equals 1. So we simply increment the frequency of that particular page by 1. All right. So let's go back to this figure and trace this carefully. So total started at 0. Right. We are currently on page 4, and the random number that we get is 0.71. So initially total is 0. It is not greater than 0.71. So what we do is we say total equals total plus this number. So total now becomes 0.47. Is 0.47 greater than 0.71? No, it's not. So we get the next value added to total. So total is now 0.49. Is that less than, is that greater than 0.71? No, it's not. So we get the next number and add it to total. So now total becomes 0.96. Okay, and the value of j is 2. But now notice that total is greater than 0.71 because total is 0.96. So this condition is true. So we simply say page equals the current value of j, which was 2, and we break. So what are we saying? So we are saying that while on page 4, the random surfer now is going to jump to page 2, right? And since he's going to jump to page 2, we increment the frequency of page 2 by 1, right? So that's how we have the surfer hop around from one page to another using the transition matrix, right? Okay, now before we continue, let me just make a remark here that this algorithm for figuring out, where a particular random number landed is what we call the roulette selection method. Okay? Roulette selection algorithm. Okay, and a way to think about this is you can think of this whole thing as representing a dartboard, where each slot has different widths depending on the value of the probability. Okay, and you throw a dart on this board, and you're trying to figure out which slot the dart landed on, right? And to figure that out, you use this roulette selection algorithm. Okay, and that's what is implemented here. Okay, now once you're done with all the moves, okay, you're out of this for loop, and then when you're out of the for loop, what you have in the hits array are basically the frequencies of landing on each of the n pages, right? And if you sum the array hits up, you're going to get exactly the value moves. Okay, so moves is spread over this array hits, and each entry there is going to store the number of times the random surfer landed on that particular page. So all that we need to do is simply iterate over that list. So that's what we are doing. So for v in hits, so this is iteration by value, and we simply print the frequency. All right, so we take v and we divide it by moves, so we print it as a fraction or a probability, right? And we print it using formatted printing up to 5 decimal places. All right, so these are basically the page ranks. Okay, and then at the end we print a new line character. So that's how the RandomSurfer program works. Now let's look at some input and output. So here, in the first instance, we run transition.py on the tiny web of 5 pages represented by this file, and we make the transition matrix, which is the output of transition.py, be the standard input of RandomSurfer. Okay, and then that's what RandomSurfer expects from standard input, a transition matrix. And then we say moves is 100 here, right? So we allow 100 moves to the RandomSurfer, and the program comes back with these ranks, right? And it's saying that page 1 is the most popular one because that has the highest rank, right? So that's the page that Google, for example, would report at the very top. Okay, because that's the most popular page. Okay, and then we run the program again, but now we increase the number of moves to 10,000. Okay, so here we get a different set of numbers, and notice that the rankings have changed as well. So here we are saying that page 0 is the most popular one. Okay, by cranking up the number of moves, we've gotten a different set of results. So the question is, what is the rank of this page? I mean, what is like the most popular page? Is it page 1 or is it page 0? Well, what we want to do is we want to run this command again with more number of moves, and we basically do this until the rankings have not changed. Right? So here we ran it with 10,000 moves. Let's run it again with more moves. So in this case, we are running the program with 10 million moves. So we get different numbers, but notice that the rankings have not changed. Right? So page 0 is still the most popular page. Right? So only when the rankings don't change that you can rely on the results. Right? So that's one way to calculate the page ranks using this idea of a RandomSurfer. Now, but this is not how Google calculates page ranks, because the RandomSurfer idea is simply not scalable, right? So even for a tiny web with just 5 pages, it takes a long time to figure out the page ranks, and it also takes a huge number of moves until you get to values that are reliable. right? And Google has to deal with pages in the order of trillions, and this approach is simply not scalable, even for Google, right? So we need a different way of calculating page ranks, and that's what we're going to discuss next. So we need to talk about a concept called a Markov chain. So Markov chain is a random process that describes behavior similar to that of a random surfer. Okay? So it's basically a random process. Now Markov chain has a very useful property, and that is the property of mixing. Okay? What this property says is that the random surfer can start anywhere on the graph representing the World Wide Web, and it really doesn't matter where the random surfer starts, because the probability that the surfer eventually winds up on a particular page is the same for all starting pages. Okay? So that's the property of mixing. So it's basically saying that it doesn't matter where the surfer starts. If we allow the surfer many number of moves, the frequencies or the number of times that the surfer will land on each particular page will not differ, right? It's going to be the same regardless of where the surfer started. Okay, so that's the property of mixing, and we're going to use this property of mixing to implement an efficient algorithm for figuring out page ranks. So what we can do is we can use what is called the power method to obtain the probability that this random surfer will move from page I to page J in 2 moves, okay, which is denoted as such. So this is the probability of going from page I to page J in 2 moves. We can calculate that using the power method by simply squaring the transition matrix. Okay, so if we take the transition matrix and multiply it by itself, we get a new matrix which is also n by n, and the ijth entry there simply is the probability of going from page I to page J in exactly 2 moves. Okay, and that's what is indicated here. This 2 denotes the number of moves. So how do we calculate the product of 2 matrices? Well, this is how we do it. The ijth element of the product is simply calculated as the dot product of the ith row of the matrix with the jth column of the matrix, right? So that's this notation, the ith row, jth column, dot product, and we know how dot product works. Okay, so the dot product of these two guys gives you the ijth entry of the resulting matrix. Okay, so here is an example. So this is the transition matrix P for the 5-page example that we've been considering. And here what I'm showing you is simply a product of that matrix with itself. Okay, so this is the transition matrix. We are looking at the product of the matrix with itself. Okay, so how do we calculate a particular entry in the result? Well, let's focus on some entry. So let's say we are looking at this guy, which is at index 0 and 0. How do we calculate this? Well, we calculate it as the dot product of this row, the 0th row, and the 0th column. Okay. So this number is simply this number times that number plus this number times this 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 number. So that's how you calculate this one. Let's take another example. How do we calculate this number? Well, that corresponds to the dot product of this row, okay, and this column. So this number 0.45 is calculated as this times that plus this times that plus this times that plus this times that plus this times that. Okay, so that's how we calculate each entry in this matrix, right? Now, before we proceed, let's talk about why is it that a dot product of a row from here and a column from here gives you the probability of going from page I to page J in exactly 2 moves. Okay, so for that, let's focus on this particular row 0, and this particular column, which is column 0, right? And so what we are doing is calculating the dot product of this row and this column to figure out this particular entry. And that we are saying is the probability of going from page 0 to page 0 in 2 moves. Okay. So if you're allowing the surfer 2 moves, what is the probability of going from page 0 to page 0? Well, in the first move, the surfer can stay in page 0. Okay. So in the first move, the surfer just stays on that page, and then in the second move, again the surfer just stays on that page. So that is one way of getting from page 0 to page 0, okay, in 2 moves, just staying there, right? That's one possibility. Another possibility is for the surfer to go from page 0 to, let's say, page 1, and then from page 1 to page 0. Okay, that's another possibility, right? So in the first move, go from 0 to 1, and the second move, go from 1 back to 0. Another possibility is in the first move, go from 0 to page 2, and then from page 2 to page 0. Okay, and then another possibility is from page 0 to page 3, and then page 3 to page 0. And then finally, the last possibility is from page 0 to go to page 4, and then go from page 4 to the page 0. So what is this sum that you see on the right hand side? P00 times P00, so that is this times that. P01 plus P01 times P10, P01 times P10, which is that, plus P02 times P20, which is this times that, plus P03 times P30, which is this times that, plus P04 times P40, which is this times that. So, and that is basically the dot product of this row and this column. So that's why we say that the dot product of the ith row and the jth column simply gives you the probability of going from page I to page J in exactly 2 moves. Okay? And now in general, the probability that the random surfer will go from page I to page J in T moves, not just 2, but in T moves, is simply given as the product of the transition matrix with itself T times. Okay, so it's simply P times P times P and so on. And this is done T times, which is P to the power T. And hence the name power method. Okay, so if you simply take the transition matrix and multiply it T times, you get a matrix which is also n by n, and the ijth entry there is simply the probability of going from page I to page J in T moves. Okay. Unfortunately, matrix multiplication is very expensive. So we really don't want to figure out page ranks as a matrix multiplication, okay? Because it's very expensive. But fortunately for us, because of the mixing property which says that it doesn't matter where the surfer starts, what we can do is we can simply make do with relatively inexpensive vector matrix multiplications. Okay, so matrix multiplication is expensive, but vector matrix multiplication is inexpensive. Okay, And that is going to work only because of the mixing property that says that it really doesn't matter where you start the surfer. Okay, so no matter where the surfer starts, if you go about calculating p to the power t, all the rows are going to end up with the same values. The frequencies are going to be the same because of the mixing property. Okay, so if all the rows of this particular matrix are going to be the same, why even bother doing matrix multiplication? Just do vector matrix multiplications, which will simply give one of the rows at the very end, okay, consisting of all the page ranks. And that's what we're going to do. That's what we're going to implement in our code. So let's take a concrete example. So going back to our tiny web with 5 pages, let's say we start with this vector, okay, where the first element is 1 and the other elements are 0. So what we are saying here is that the random surfer starts on page 0. It really doesn't matter, we can start the surfer wherever you want, but in this case we are starting the surfer at page 0. If you started the surfer at page, let's say 3, then this initial vector is going to be this 0, 0.0, 0, 0.0, 0, 0.0, 1.0, and 0.0. Okay, so we start the random surfer at page 3. So you can start the surfer anywhere, but in this case we are starting the surfer on page 0, right? So that's our initial vector. So what we do is take that initial vector and we multiply it with the transition matrix P, which is what is shown here. And what we get as a result is another vector. So vector times a matrix gives us a vector. Now this multiplication is absolutely well defined, because this vector has dimension 1 by n. This matrix has dimensions n by n, so the inner dimensions agree, so you can carry out this multiplication, and the resulting vector is going to have dimension 1 by n. So that's what you see here, 1 row and n columns. So now the question is, how do you calculate an element from here? It's exactly the same idea that you use to do matrix multiplication. So each entry here is the dot product of this vector and the corresponding column. So this column is the 0th column, so it is obtained as the dot product of this vector with this column. Okay, so 0.02 is that times that plus that times that plus that times that plus that times that plus that times that. How do you obtain, for example, this number here? The same idea. It's the dot product of this guy with this column. Okay, so this number is simply that times that plus that times that plus that times that plus that times that plus that times that. Okay, so that's how we obtain this vector here. Now the question is, what are these numbers? What do they denote? Well, they specify the probabilities that the random surfer winds up on each of these n pages after exactly one step. Okay, so by doing a vector matrix multiplication once, you get the probabilities that the surfer winds up on each of the pages in one step. All right, and if you if you look at these numbers carefully, it is basically the first row from the transition matrix. So that's what you get after one round of multiplication. You just retrieve the first row of the transition matrix, and that makes perfect sense, because what is the first row of the transition matrix? It tells you the probability of going from page 0, which is where the surfer started, to any of the other pages in exactly one move. Right? Okay, so that's after one step. What if we want to know the probabilities of going from page 0 to the other pages in 2 steps? Well, you repeat the process. Take the vector that you got from the first multiplication, so the result of the first multiplication, which is this, and multiply it with the transition matrix again to get a new vector. Okay, and how do we get this vector? Well, again, it's the dot product of this vector with the corresponding columns. Okay? So this number, for example, is obtained by taking the dot product of this guy with this column here. So it's this times that plus this times that plus this times that, plus this times that, plus this times that. So that's how you get that number. Okay, so what is this vector now? Well, it represents the probabilities that the surfer winds up on each of the n pages after 2 moves. Okay, so what if you want to figure out the probabilities of going from page 0 to the n pages after t moves? Well, you repeat this process exactly t times. All right, so that's what is mentioned here. The vector giving the probabilities that the random surfer is at each page after t steps is simply the product of the corresponding vector for t minus 1 steps and the transition matrix P. Okay, and that resulting vector that you get after performing t vector matrix multiplications is simply a representation of the page ranks provided t is sufficiently large. All right. So this is the idea that we're going to use in our next program, right? That we will be using to calculate page ranks. So that program is called Markov.py, and the input to this program is similar to RandomSurfer.py. It takes a command line argument called moves. Okay, that's the number of matrix vector multiplications that we want to perform in this case, right? And the other input to this program is standard in input, which is the transition matrix, right? So it's basically the output of the transition.py program. So we give moves as a command line argument and the transition matrix via standard in, and what the program does is it simply writes out the page ranks, right? So it computes the probabilities that the random surfer lands on each page after moves number of matrix vector multiplications, okay? And it simply writes the page ranks to standard output. So let's go through the program. We import the usual modules, std array, stdio, and sys, and then we get the command line argument moves, and then we read the transition matrix into memory. And this code is identical to what we had before in RandomSurfer.py. So I'm not going to go through that again. Okay, so once this code is done, this matrix probs is populated with the transition matrix. Okay, and then what we do is create a one-dimensional list called ranks of size n, everything initialized to 0, and that's the list that is going to store the page ranks, right? And then we say ranks at 0 equals 1. So if n is 5, after this step, ranks is going to be a one-dimensional list, that is that. Okay, so this is the initial vector that we talked about. So here we are saying that the random surfer starts on page 0. And again, it doesn't matter where you start the surfer, but we chose to start the surfer on page 0. Okay, so that's the initial vector. And then what do? Well, in this for loop, we simply carry out moves number of matrix vector multiplication. Okay, so let's go through this. So I goes from 0 through moves -1, and then we say new ranks. This is the resulting vector that you get from matrix vector multiplication. So new ranks is simply a list, a one-dimensional list of size n, everything initialized to 0, and then j goes from 0 through n-1, and k goes from 0 through n-1, and we are simply saying that the jth element in new ranks is simply the old value of that element plus the product of ranks at k times probs at k j. Okay, so what this loop is doing is it is simply calculating the dot product. Okay, so it takes new ranks, which is a vector. It takes ranks, which is a vector, and it multiplies it with the transition matrix to get new ranks, which is a vector. All right. So it simply calculates the dot product of these elements, with the jth column to give you the jth element here in new ranks. So the jth element in new ranks is calculated as the dot product of ranks with the jth column of the transition matrix. Okay, so this is ranks, this is the transition matrix P, or in this case given as probs, and this guy is new ranks. Okay, so the jth element here is simply the dot product of this vector and the jth column of the transition matrix. Right? Okay, and then once a new ranks is calculated, we say ranks for the next iteration is new ranks. So this now becomes the new vector that you multiply with the transition matrix in the next iteration. Okay, so that's what we are doing here. And once we are done with this for loop, ranks has the page ranks. So all that we need to do is iterate over its values, which is what we are doing here, and print those values out. And here we are using writeF to print the page ranks up to 5 decimal places. Right? And at the end, we write a new line character. So let's look at some input and output. So here we run transition.py on the tiny web of 5 pages, and we make the transition matrix be the input of Markov.py, which is this program, and we say the number of moves is 20. Notice that moves is much smaller than what we used in the previous case where we looked at RandomSurfer.py. So there, even in the first run, moves was 100. Here it is much smaller than that. It's 5 times smaller than that. Okay, and yet the numbers that you get are comparable to what we got with 10 million moves with RandomSurfer. Okay, so the numbers are comparable, and more importantly, the ranks are identical to what we got with 10 million moves there. Okay, so we are saying that page 0 is the most popular one. Right? And then we run this program again, but now with moves set to 40. Okay, and the numbers change, the values of the ranks change, but the rankings is still the same. So we are still saying that page 0 is the most popular one. All right. So this approach to calculating page ranks is way more efficient than using RandomSurfer.py. Okay, and this program is very scalable, and this is the idea that Google uses to compute the page ranks, right? Because this is a scalable solution. You can use this approach of matrix vector multiplication even for huge number of pages, right? Okay, so that concludes this lecture on Google's PageRank algorithm. Thank you for your time.